Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So it's my pleasure to introduce Percentiles. He's a PhD candidate from Princeton. His advisor is Professor Margaret Martinosi, and he's going to talk about his interesting work he did in the ZebraNet project, where they instrumented zebras in Kenya to track their behavior. Okay.
Thank you for the introduction. So what I'm going to talk about is going to talk about collaboration in this very sparse network. So basically, how do you collaborate in a network where you may not always have neighbors? So why am I talking about this? Well, recently, mobile phones have become all the rage. Computers are becoming increasingly ubiquitous. In fact, I think in some countries, penetration is already up to 120%. A lot of people have two phones. So computing are becoming increasingly mobile, and they're pretty distributed. And with mobile phones, a lot of devices are actually computers nowadays. That gives us a lot of opportunities. When computers are everywhere, we have lots of sensors. Now, basically, everything does a little sensor, right? So we have sensor devices everywhere, so we can actually collaborate and do opportunistic data gathering and sharing, as well as integrative data mining and collaboration. So in a beautiful cityscape like New York City, I hope that's what this is, there's going to be many, many nodes in here. So what can these nodes do? This node can actually communicate and produce this beautiful mesh network. So of course, there are a couple problems. Nothing's without problem if you want to do research, right? Devices, these nodes, actually they can move. And they can move to sparse areas. They can move to areas outside your intended deployment area, like outside the city or outside your block. And radio ranges relative to these movements are pretty small. So what does that mean? That means I just lied to you. That means instead of that beautiful picture, you get something like this. And maybe a little later, you get something like that. The connection constantly changes, but you pretty much have a sparse network. So if you want collaboration in these networks, you really need nodes that actually work in various situations. You need these type of policies. So basically, something that works in full connectivity, dense networks, you have lots of neighbors. You have some connectivity. You have a few neighbors where you can talk to, but you have mostly connected nodes. And then infrequent connectivity, very sparse situations. And also the absolutely no connectivity, very, very, very sparse situations. So what current work mostly focuses on is actually this fully connected to some connectivity area. So nodes mostly can talk to somebody. And what my work actually focuses on is pretty much things that work everywhere. So whether you have full connectivity to no connectivity, there's some kind of functionality you can provide. Well, let's say periodic. So I should actually move this thing a little bit over. But yes.
Would you consider one node in that white section if you're the only node there?
So as you can see, I'll have some type of functionality even with one node. It just won't be very good.
All the way to the right, one node.
Yes.
Okay.
So what we have is, so what type of applications will actually have this type of characteristics? Well, I would like to argue future mobile phone applications. Basically, anything mobile and ad hoc will have these kind of things. Future mobile phone application being one. You can free up the bandwidth bottleneck by having ad hoc communications. In fact, China Mobile, I forgot the exact name, but Mobile China, or like the conglomerate there, they're actually looking into how to actually charge in this type of ad hoc communication future. How do they actually communicate and charge for that service? They're actually looking into that. In developing regions where there's a lack of current infrastructure, you really need these type of systems. And in mobile sensor networks, like for animal tracking, you just can't tag all those many animals because that'd just be mean, right? And it's really difficult deploying infrastructure in that area as well. So what I'm first going to look at is actually this animal tracking application. Well, because it's actually a very compelling application where you really require this type of sparse functionality. And it happens to be where I actually started my research, so it's actually very convenient for me to start. So in this talk, the focus will be mostly on improving the functionality of sparse mobile networks through collaboration. So collaborative data gathering, what we actually did for ZebraNet. Collaborative localization, or LOCALE, well, I'll just show you the system overview, the hardware implementation, and simulation for that. And finally, I'll give you sort of my view of the future. So ZebraNet wildlife tracking, what is that? Well, basically, so my research actually started off here. So we set out to solve the problem of animal tracking, more specifically zebra tracking. So ZebraNet is actually a mobile sensor network project where the goal is actually to track wildlife in very remote areas. So from the biologist's perspective, what they want to do is actually they want to track animals over very long term and over very long distances. Basically, the question they want to answer is what are the animal behavior both interspecies and intraspecies? Like how does animals, different herds of same zebras actually push each other, whether they hate each other, whether they like each other, whether maybe like a predator, is the predator pushing the prey or is the prey leading the predator? And also interspecies interactions, like how does human interact with these animals? Basically, how does my herding my cow actually kill off these animals, maybe make them starve to death? So you can see the answers to these questions have very high impact in land use issues, which many times where human needs and animal needs are in conflict. So, but the problem with them is that the existing technologies are just very lacking. So what they have is these little VHF collars where they put a collar on an animal that goes beep, beep. So these people actually need to drive around with these antennas, actually listen to where the beep is stronger and find these animals before they can actually track them. So they'll be lucky to actually get 2 location fixes per day per animal. Per animal meaning 1. And there are also other store and retrieve trackers like the GPS and the satellite trackers. Those things are very expensive, but provide them with more detail in the term of 4 data points per day. So for us, yes, because they actually want to track over a couple months, and they don't charge, so the battery actually, right. So for us, actually, our goal is actually to, well, get data, get fine-grained animal movement data. What does fine-grained mean for us? We want to get them 8-minute interval GPS locations with the timestamp. So that's much finer than what they have. And we want to use minimal energy because, well, we want long-term operations because it's really hard to charge that at Zebra. So we look at how do we actually do this. Well, we can look at the classical sensor network. Basically, it's a little mote that have a certain radio range. But one is probably not going to connect directly with the base station. So what we need is a lot of them. And of course, now we need about like maybe hundreds, thousands, tens of thousands of these fixed nodes. The drawback is prohibitively expensive to deploy for this application. They have very limited coverage area. We're basically limited to wherever we can throw these nodes. And if we want to monitor the environment, throwing tens and thousands of batteries out there is probably not the best way to monitor the environment. So we look at other type of networks, the more classical mobile network. So this is more like your cell phone network, where the animals will, when they come into cell phone coverage, they will make a call and upload the data. Now, one good thing is that nodes that can be mobile. In fact, go ahead.
Quick question on zebras. Do they run in herds?
Yes, they do. They
So
have
if
little
you
thing
have-
called heron.
If you deploy GPS and you have 100 zebras and each of them has a GPS that reports 4 times per day, and since they're running in herds, then doesn't that give you the coverage that you're looking for? Since you just offset when all of them report throughout the day, you really get 400 readings per day.
I'm sorry, can you come again?
So if you have 100 zebras in a herd,
Right.
and you have GPS on all of them, and
Right.
it can only give you 4 points per day, but you offset those points throughout the day, then you'll have 400 readings per day. You would have good detailed results. Have they considered that? Or what-
So yes, so if you consider a dense network, yes, that will happen. But the problem is you will have to tag all those 100 zebras in that one herd. And once they saw the first animal go down, they run away. So it's hard. And another problem is that the opium we use to tranquilize the animals is considered an illegal drug in Kenya. So we actually had to smuggle them from South Africa, and there's a limited amount we have to. So there are some hard limitations too. Go on.
Just to follow up to his question. When you have a zebra in a herd, does it tend to stay with that herd, or does it tend to switch herds? Like, if two herds come together, do they kind of reshuffle, or do they tend to stay with their own group?
No, I think that's more of a biologist problem. But from my understanding is that they do tend to stay with the herd, except for the youngins. The young males actually do leave the herd once they grow up. So you can see that a classic mobile network may be able to solve this, but the problem is that we need very dense concentration of base stations to actually get the data back from most of the animals. So one of the conclusions that we came up with was, hey, why don't we just use a collaborative way of getting this information back? So one animal may come into contact with another animal, contact meaning within radio range, and they will exchange this data. And then they may come contact with another animal, they exchange the data again, and finally, one animal may come into contact with the destination and upload everything. Now, the good thing is that we have reduced coverage requirements. All the nodes can be mobile. In fact, they have to be. And they collaboratively return the data in a delay-tolerant manner. So as long as we don't care about real time, this will work. So there are a couple challenges. The lack of neighbors, because we're encountering neighbors infrequently, really require us to be density tolerant and delay tolerant. And the difficulty to access these nodes really means that we can't really charge the batteries. So we really need we want a long lifetime and energy efficiency. So for the research side, basically I built the hardware and some of the software that enables a long-term collaborative data retrieval system. Basically, we have the energy efficient store and forward hardware. Through 6 major iterations, we have up to 96% efficient power supply for some of the peripherals. Can't claim all. We have energy scale.
You mean the energy loss through the power conversion is only 4%?
Yes. Yes. And most of the nodes, when we were building this, the energy conversion was only 40% was lost.
This is solar charging?
Yes, it was solar charging. The converter in the solar cells is not as high as 96%. But, yeah. So for our flexible solar cell, it's actually only 22. And then our conversion was 80. Go on.
So if I recall correctly, you previously mentioned that the problem with the GPS solution was that you could only collect a few readings a day because you wanted it to last for a month and it wasn't charged.
Right.
So if you were to put a solar cell on that on a GPS solution, would that suffice?
On the existing GPS solution, once they collect the data, they drop off the animal, and then somehow magically you will have to find that device. And for the satellite solutions, most of the time it's the expense of the satellite solution, the data expense. So for the energy efficient software, I developed the efficient scheduling and sleep. Basically, there's a couple of papers on that. You can read those. Other students also did a remote software update, data compression, and other stuff. But the cute thing about ZebraNet, I guess, is that we actually deployed them. We actually deployed these colors. You can come play with them later. On these animals. So we actually deploy 4 animals. The biologists actually learned, we deploy in this area called Sweetwater's Ranch in central Kenya. It's a roughly 10 kilometer by 10 kilometer game reserve. I can't speak English today, I'm sorry. The yellow here is a little fence. The blue, you can guess, is water, and other things are ground. We deploy 1 base station in the visitor center right here. The base station has the radio range roughly covering this area, basically covering this water hole and this water hole. So presumably the animal will go there to drink. So we collected these data. It's basically 4 nodes. With we put them on 4 nodes. We put them on. We got many peer-to-peer links. We got more than 5,000 location fixes through this month deployment window. So we have 4 different colors. This yellow, this green, blue, and black, and red. So what the biologists learned is actually they learned quite a bit. Before, they never had nighttime data, detailed nighttime data. They only have daytime data. Something about grassroots don't want to be eaten by lions, I suppose. So from night, but they assume that the animals just stay put. Who moves around at night? And the problem is that, of course, they don't. In fact, they move a lot at night. So they thought, okay, the animals must be afraid of lions. That's why they didn't move. And it turns out that wasn't the case. They actually move into the bushes. So you can see, actually, these movements through the bushes are mostly all done at night. So that was actually something they did not expect. And furthermore, just to show you how much they discovered, just one example here, the red animal. They've been observing this animal since her birth. They know when she was born, when she took her first walk, who she was dating, who she broke up with. But they never knew that she crossed the river. And in fact, in the first month, she crossed the river quite a number of times. And presumably to cheat on another zebra, but go on.
Question. Do you have a GPS device on that?
Yes, each node have a GPS. So that's how they collect the data. So, they discover a whole bunch of things that previously nobody knew. But for us, actually, we discover a whole bunch of things too. Well, first of all, it's the first fully mobile sensor network that's ever deployed. And we actually discovered that, hey, the store and forward idea actually worked as advertised. Something in research that probably never happened before, I'm guessing. But even though that's the case, the radio was, the dynamic of the radio connections changes quite a bit more than we expected. Basically, when the animal look at you, you get 1 kilometer that way. When the animal lower their head to eat, you get no connectivity. So just a pure blowing of the wind will actually change your communications from full connectivity to actually no connectivity. It's exciting for researchers, but frustrating when you're out in the field. So we actually learned a lot from this. And this project actually had quite a bit of impact. So we have, in the developing regions, we have the AIR project, where actually I use delay-tolerant collaborations to obtain voice recording from enable women's contribution to the local community radios. Mostly women have worked in the field. But now, while they're working, they can actually communicate to the radio. So they can do a little recording, and it hops to the radio station and where it actually gets sent out. In United Village, the United Village project actually enables store and forward local internet access. And in sensor networks, there's more than 200 projects in the polar regions alone. And livestock tracking is coming. It's in Australia, they're doing a lot of those stuff. And various other cute animal nets and turtle nets. I guess that's not one of the cute animal nets. But anyways, so go on.
How many readings did you lose because of the store and forward limitations?
None, because the flash drive actually never filled up. in that 1 month window before the animals destroyed everything. And we didn't intend to deploy 1 month. We actually intended much longer deployment. But the animals are too nasty. They chewed on the solar cells, and eventually the solar cells all got ripped off. And basically there was we were lucky. It's a side story, but we were lucky. The people who work on elephants, they have wire reinforced collars, and they just get them off whenever they want to. It's an elephant, right? So for us, it was actually stay on a lot longer than their collars, but similar.
Did you assume that the collar was uncomfortable for the animals?
So our first version was uncomfortable for the animals. We see them shaking even after 1 year. The second collars was much more comfortable. It was only the first day where they shake their neck, but afterwards it was fine.
So was it the case like in your motivating example where you had the 3 zebras and one goes around and talks to the others and then goes back to the base station? So was it the case in your readings that it was mostly like a very small number of zebras that you had instrumented that communicated directly with the base station?
Actually, the black, green, and blue all have at one point communicate with the base station. But if it weren't for those animals, this data will never actually get to the base station because they're always behind the coverage. So yes, so because of the delay tolerance, we were actually getting this. But as you see, the animals actually move around quite a bit more, so there was a lot more mingling between these animals as well.
I'm sorry, I'm confused. You said the flash drive could store all of the readings for an entire month?
Yes, we have a lot of compression. Like the animals didn't, when they were eating, they weren't moving that much.
So why did you need store and forward at all? And as long as the zebra returned one time, you never needed them to talk to each other. They just needed to.
Well,
the red one never does.
The red one never did. The base station is right here. It never actually got anywhere close. Not only that.
You could just go out one time to catch that.
Yes, that's assuming you know where the animals are.
But once per month, you just need to find each animal once per month.
Yes, but it's a 10 kilometer by 10 kilometer area. So you're finding this animal where they actually know where they are. This animal stay put all the time, and they can actually find them about once a month. So, and you can imagine these animals, if never walked into this area, we're pretty much never going to see them again.
Total population, or do you have a feel for the total population of animals in that region?
If I remember, it was about 2,000.
You had about 4 out of 2,000.
Right, but we only have 5 tranquilizer darts. Again, due to the limitations. Well, there's a lot of problems when you actually do real deployments on other limitations. So moving on from ZebraNet.
About the radio issues. You said when animal is moving about, the neck is moving about, you actually
right, so we were actually never. So we actually never actually modeled that into something formal. It was one of the best lessons we learned, but we didn't really know how to model it, so we didn't.
Can't you use that information as a way to model the behavior of the zebra as well? You actually have the location of 2 nodes, and based on the link quality, can you actually say something about it?
Perhaps, but it's very short windows. So we actually were able to learn more with onboard accelerometers. So we had limited tests with accelerometers on certain animals.
So what are the sensors you have then? You have a location GPS.
So in the field deployment, we only have GPS, and that was it. But in some other nodes we built, we also have accelerometers. And based on that, the eating and stuff, it was much more finer grained information we can actually get than the actually just rare communications we get. Because the animals really were in range fairly rarely.
And assume the solar panel is actually on the top of the neck, or could that be an issue once it's actually underneath the...
So it's actually on the side, the GPS was on. Oh, I have it right here.
The GPS is, where's the GPS?
The GPS antenna is actually on top, right here. And solar cells on each side, and your radio antenna on bottom.
And you assume that when when the animal is shaking the neck, it's not going to actually
so
move
the rotation,
such that it got to the bottom of the neck.
it does move around sometimes, but it's fairly soft up here, so it's more comfortable for them to actually make it sit up here. So actually, they do tend to actually rotate it back.
Antenna at the bottom.
Because the GPS had to be on top, and we didn't want to deal with interference issues. Okay, moving on from ZebraNet. So we learned actually many lessons from the deployment. One thing, the collaborative data passing actually worked pretty well for static sensor data. Data that did not change after you collect it. But what about dynamic data? So what kind of dynamic data am I talking about? Things like system energy. What is the average battery power of the system here around me? Sensor calibration. How do you calibrate potentially many sensors that are measuring actually different things? And mobile node localization. How do you actually estimate the node's physical location and maintain this accuracy? And you can imagine these are difficult problems in dense networks. But in a sensor network, in a network where actually you don't have any connections most of the time, how do you do this? Well, so I'm going to talk about mobile node localization. Again, out of convenience. It's actually the most recent work, so I'll tell you that. So what is localization and who cares? Localization is actually getting the accurate physical location, physical position information for a mobile node. So why does it matter? Well, a lot of things requires it. For example, E911, SDC is actually requiring all cell phones to be able to self-localize when making a 911 call. Social networking. There's already an application out there where you can track your friends 24 hours a day. What about privacy issues, you ask? I don't care. Geographic protocols. For example, you may want to route something away from the microwave, maybe in a military or home situation. Spatially aware applications like animal tracking or traffic management or mapping. Google is sending out GPS kit out into the field to map rural areas in India where they don't have good maps. So I'm sure Microsoft will have something better than that. So why don't we just use a GPS then? Well, there are mount location limits. It doesn't work well indoors. It's very difficult in this new buzzword, urban canyons. And antenna really should be facing up for best reception. That means cell phones in pockets, in bags, probably won't work that well. And it's expensive. You have one GPS unit plus one antenna per device. And it's power hungry. How power hungry? Well, here's the breakdown of our power usage for the ZebraNet nodes. We got the GPS, the radio, and the processor, and everything else. So you see the processor and everything else only use 3 microamps. The radio use on average 3 milliamps. The radio on average use 7.3 milliamps. The GPS with one sample every 8 minutes use roughly 8.3 milliamps out in the field. Milliwatts, sorry. And that's not considering the continuous GPS, which use 66 average milliwatts. And GPS, so what we get is actually obtaining this location. It's just very, very costly. In fact, it's the most costly thing in our node here.
What was the average power output of your solar cells?
It's actually 50 milliwatts, 50 milliamps at 3 volts, so 150 milliwatts per this area.
Okay.
But that's facing the sun directly. So of course we're on the side. In real life, if I remember correctly, it was about 50 milliamps and 3. So basically one cell facing up. 6 cells turns out to be about 1 cell. Basically,
You get 150 milliwatts is what you said?
150 milliwatts.
Milliamps.
Right. So basically, it's only 3 cells are facing sun, and during the midday, where the sun is intense, it's on top, so we don't get a lot of things.
The aggregate during a regular day is 150 milliamps
150
during normal
milliamps.
insolation.
So 100 to 200, something like that. It's around 3 volts. 150 milliwatts. 50 milliamps at 3 volts, 150 milliwatts. I'm confused there.
GPS is quite low for a cell phone, right? I mean, a cell phone's average power draw is what, like 800 milliwatts?
Right, I believe.
At that base power, this is a minuscule power budget for a GPS.
I'm sorry?
Cell phones are probably 8, you mean when it's transmitting?
When it's transmitted.
Yeah.
Okay, most of the time they're not transmitting. But this
Sure,
Most
with the
times
screen,
yes.
I mean, we'll like an iPad with the screen on without transmitting is like 500 to 800 milliwatts.
So to give you an idea, a regular cell phone that lasts about 4 days standby lasts about roughly 4 hours when you have the GPS on continuously. Right. Of course, their GPS is different from our GPS. Our GPS at the time was the lowest power GPS available. So.
How much overkill was there at an 8-minute cycle? I know that you wanted compressed temporal readings, but that seems awfully short. 8 minutes.
It's extreme overkill. So in fact, the first thing the biologists wanted one sample every 1 minute. We say we can't do that, power limits.
Because reacquisition of GPS would eat that up, so you'd have to have it on continuous.
So actually the reacquisition was only about 30 seconds.
Yeah, but you're still on the order of continuous anyways. Yeah, that's way up there.
1/16 essentially.
But yeah, duty cycle is your friend. You can
Yes, if we can reduce it, yes. So that's why I have the localization work. Yay, collaborative. Yes, so solar cell actually charges the battery.
How big is that?
It's up 2 amp hours. Right.
Have a power problem, right?
Not at the beginning, but soon, like
Solar cells.
when they started. Right. Well, first of all, they licked it, and saliva and the many dust just settle on top. Then we just, whoosh, and then they start chewing on it. But
Or the zebras just in the evening or at night.
so actually more mobile than during the daytime. During the daytime, they actually ate, and during very hot hours, they actually did not move. But so how do we actually lower this power consumption? Well, collaborative possibilities. There are triangulation methods. So first you discover the topology of your network. But the problem is there's a large overhead whenever the network moves. Every time it moves, the topology changes. You have to rediscover the topology. And it doesn't work when you don't have connections. So that's out. So we can also receive location information from beacons. Some cell phones use that. In the UK, they can localize down to roughly half a kilometer. So, but the problem is, again, large infrastructure costs. And another thing is there's some proprietary access to the tower, so we may not actually get that. Also, collaborative localization that's used in some dense robotic networks. Like a couple of robots will collaboratively localize a little soccer ball. So my work is actually to apply this collaborative localization into a sparse mobile sensor network environment. So basically no Linux, or I mean mobile Windows. So I developed this delay-tolerant collaborative localization service, LOCALE, which stands for Low-Density Collaborative Ad Hoc Location Estimation, basically made up for the acronym. The goal is actually for low power and low cost, both device and infrastructure, and it's supposed to work everywhere. So the idea is actually fairly simple. We have one node that's traveling and asks, "Where am I?" And a beacon comes up, says, "Oh, you're on the corner of Main and 2nd Street." A little bit later, the two nodes actually may come into contact and ask each other, "Where am I?" But no one knows. But they've been tracking their movement since Main and 2nd Street, I believe. So they know one thinks I'm around 12 at Main, and another thinks I'm around 14 at Main. Well, the tracking, there's a little bit error in the tracking. So they together figure out, oh, we must be on 13th at Main. That's the basic idea. But the key issues are how do you aggregate this multiple position information into a single one? How do you estimate the confidence in this estimation so you can combine them more accurately? And how do you track position between encounters?
Do you assume you can track the direction, the traveling direction?
Yes. So basically, 6 degrees of freedom, you need maybe a 3-dimensional compass or a 3-dimensional accelerometers or gyroscope, whatever. So the basic idea is actually we want to reduce the reliance on per node GPS with peer-to-peer information swapping. And to do that, we have a two-dimensional normal distribution for this location estimation, with a mean to be the estimation of location and the estimation accuracy being its variance. And I'm going to skip that. So nodes track movement when they're actually, well, moving. Do you want to? We're a little late. So it's just basic. Thank you. So nodes track their movement where they're moving. One node may actually move, so it increases their variance, lowers their accuracy. Another node may move a little further, increase their variance, lower their accuracy. And that's the local phase. Basically, okay, just to scare you. But the basic idea is actually, don't worry about this. Track movement until you meet a neighbor. Track movement until you meet a neighbor. That's it. Don't worry about it. It's in the paper if you want to know details. So then they merge once they come into contact.
So you assume the variance is isotropic? We don't have some distributions or skewing?
Actually, I do assume they have skewing.
So they do have skewing?
They do, but I just represent it in circle form to be simple.
Two-dimensional Gaussian?
It's two-dimensional Gaussian, and it's very easily extended to three-dimensional. Just basically increase the dimension of the matrix, right? So the idea is that when the two nodes are in range, we want to exchange the information from the neighbor's estimation to my local estimation. So to do that, we need both distance and the relative angle, relative direction between these two nodes. But we may not have that. What if we don't have the angle data? Well, in those cases, we can just use the estimation of location to get the angle data. Then we just sort of stretch it in the vertical direction to actually do this. Of course, there's a correct way shown in the paper. Don't worry about that here. The idea is that we want to do a self-estimation. We combine that with the information we receive from the neighbor stretched in a correct way based on the error model from the distance measurement and from the angle measurement. So basically, the stretching is done right here.
Could you go back? So how do you obtain the distance estimate?
So the distance estimation you can obtain with your signal strength, or we all know signal strength is pretty bad, or we can actually do that from just being in range. So if you're in range, if I can talk to you, you're at a certain distance away. You're at a certain distance away from me with a certain variance, right? Basically, if you're in Beijing, you're not in range. So if you're in range, you're probably somewhere near me.
How do you deal with the fact that these sensors, in the sense that antennas might be oriented in an interesting way, such that you may not have these, again, isotropic propagation model?
So in those cases, then I would sort of rely on this error model to be accurate. So
just make it a very large variance.
Very large variance, right? Or if you can, you will actually have to bend it in certain directions based on your variance, because variance is also two-dimensional in this case. So you actually shape it. Of course, since I do assume normal.
What's the granularity you concerned about in this case?
Granular.
What's the accuracy?
So accuracy, I'm going to show you how accurate this will become. But basically, I'm sort of talking about building-wise, not like meter-wise. So once you get actually the stretch thing, you can then merge, and you actually get two different distributions. And of course, you see that because of merging, it's becoming an ellipse, so not necessarily circle. The merging is actually you want to merge the variance and the mean. The variance, you can think of it as merging two parallel resistors. The mean is sort of like your geometric mean. That's basically the takeaway message from this scary graph. So once...
Can you go back?
Sure.
Is this actually just like common filtering?
Yeah, it's very much like common filtering.
Except that you don't have the dynamic time stamping, but just the iterations over the Gaussians.
Whenever you meet, you sort of update, and in between you guess.
So you need to invert the matrix. It's pretty
yes,
expensive.
It's pretty expensive. but we're going to see implementation of it.
It's just a two-dimension in this case.
C is two-dimension, but we're going to see a implementation of this on some data from the implementation on a 4 megahertz integer processor. 4 megahertz.
That's the processor
on these things, right? So, go on.
I have a question about this merging process. So, for node A, I have some information based on like I talk to a locator, I know my location, I travel, I track my direction, I track my speed, I have my estimation. Would it be possible after the merging with another node, actually I lose the accuracy on my location information because I was confused or get more noise? You see what I'm saying? Merging process doesn't help.
Right, so what I'm assuming here is everyone is subject to the same probability distribution of this noise and error. So once you combine with more sample size, you can, from just basically the, what is it called? Well, basically you actually get more and more accurate because you increase the sample size.
I was thinking there may be some decision processing. If that node is too
accurate,
get that information, then use that to...
Right. So this type of security issues, like what if a node is actually just trying to mess up your system, just purposely having some wrong things. I did not look into that, but I do have some results from when a node is actually incorrect.
But I think the point was actually that you can actually look at these additional measurements you get from these exchanges and looking at the quality of the data. So do you have some way to, say, rank them and throw away those that are obviously an outlier or things that does not really contribute to the accuracy?
So the rank is based on the variance. So if you have a very small variance, that means you're very certain. Then I take you, when I combine, basically I will take the variance into consideration. So basically, if you have a very unsure, then I'm going to be, not looking at you very well.
You can look at this ellipse, right? And measurements along this longer axis is much more useful because that's where the error is much more, much more prominent. But in this direction, it's much less. So you must have some geometrical ways to actually look at it. Say, I need to get some information in this direction to actually shrink the errors.
Right. But we cannot control the movement, so it's basically pretty random. So when they come into contact, right, there's a two-dimensional thing, and when they combine, they actually do take the ellipse into account. They don't assume a circle. So after they meet, they combine, they continue. One node may actually go away. Another node may come into contact with the GPS station and merge with the GPS station. And later on, these two nodes might meet, and they merge. So even though Lisa never met the GPS, Bart was able to actually spread this beacon information. So locale basically spreads that. So basically, we have three phases. One is a local phase that operates between encounters. The transform phase and the update phase are when they meet a neighbor, transform from the neighbor's location estimation to an estimation on my location. And the update phase combines the distributions. So here is actually the entire merge phase together. But don't worry about it. It's the details in the paper. Practical issues are the projection. How do you actually project the local estimation into from your neighbor's estimation into your own local estimation? There's also a description of how do you actually correctly rotate this estimation into different coordinate systems so you can actually correctly merge these things. How do you handle circulation information flow? For example, if I'm walking together with someone else and constantly merging with them, then I can get an inaccurate, falsely accurate estimation. And then also implementation on 4 megahertz processor, other statistical math issues are all handled in the paper. But here's a merging example. Basically, we have one that's very unsure, one that is very sure of its location estimations. And when this is probably your question. So when these two things meet, they were based on, because it had distance information, not quite the angle information, it will give this ellipse. So it changes very little in the vertical direction because it's pretty unsure of the angle, but it changes, the most changes in this horizontal location, horizontal. But one thing to note is that variance is also reduced in the smaller one, because they actually gain information. And whenever you gain information, you actually reduce your variance. But since the information I got was pretty bad, you actually won't notice that change. So we implemented this thing on ZebraNet sensor nodes. Basically, that little 4 megahertz integer processor. Terrible, terrible idea. Rudimentary movement tracking was implemented on this thing. It tracked movement with a accelerometer. That algorithm that I developed in a day give you about 15% error on car and while you're walking, based on your distance you moved. Based on the distance you moved. Right, so roughly 15%, a little more in the direction you move, but roughly 15%. Pretty big, the idea is.
So this is in position?
This is in position tracking, just movement tracking, just with the accelerometer.
Okay, that's a lot better than anybody else in the world's claiming.
So other people I've seen have been claiming for 2%, but this is actually a fairly special case since I'm holding it like this, I'm driving in fairly straight lines.
Like the standard claim is over, I don't know, about 10 seconds you're off 4 or 5 meters, and over a couple of minutes you're off many kilometers.
So yes, that's probably the case since we're actually moving fairly fast, since I'm walking in one direction.
I'm saying those are the errors just due to offsets, because your offset is not a position offset, it's not a velocity offset, it's an acceleration offset. So
right.
Without ground truth, you have no idea what your acceleration offset. So that's
so
why
because of the movement, so we start off by standing still, and actually periodically when it senses that you're standing still, so my algorithm, so it actually resets. Yes, every now and then.
Which is how often?
So it's about, the communication is actually once per minute, so the ground truth is also once per minute.
That still seems awfully good.
So the paper I saw was they actually did 2%. So
Okay, I think they had something else going on there.
they actually use a gyroscope too.
Because 2%, I would guess you'd have to have ground truth every couple of seconds.
Perhaps. So I just saw the 2%. But we do get roughly about 15% driving in one direction. So I guess acceleration is fairly constant. So there is actually one bump in the street, but basically that's it. So the hardware test is actually 2 cars driving toward each other. After 300 meters, they meet and merge. Well, yeah. So this is a result from 10 runs. Without merging, the error is actually 48 meters. With merging, it's actually 21 meters. So I say fairly okay. So with locale, even in this, keep in mind this is just one-shot example. Basically, it already is reducing it by 2x. Oh, reducing by 1x. But the thing is to note that the code overhead, the movement tracking is actually giving us 190 millisecond code overhead. So periodically, we actually include this merge tracking into the estimation. We're actually doing that once per minute. And we're also merging. So the merging process, that also happens once per minute. It's taking half a millisecond. Attempts to happen. Only happens when there's a neighbor. So even in this case, it's roughly okay for a person who's probably walking, something like that. But the cute thing is, well, the cool thing is, maybe not so cute, the power comparison. So with locale giving you continuous location estimation, you only consume 430 microwatts of power. With one sample every 8 minutes of the GPS, you're in the lab condition, you're assuming 4,100 microwatts. And with the GPS on the continuous, you're actually using 66,000 microwatts. That's 153 times more energy than continuous with continuous locale. So what we get is much better energy profile, which means that we can actually use this in conjunction with the GPS. So since we actually know our error estimation, the variance, once that grow, we can actually just turn on the GPS. So that's just a small scale thing. We did some simulation based on the data we collected. Basically, we have a beacon in the center of the field, some couple nodes around. Each one is 1 kilometer radial range, uses only in-range and out-of-range information. So locale nodes merge with all merges with all nodes, including the GPS, and track its movement. The beacon and directing system only merges with the base station, which is GPS station, and not with other nodes, but everything else being the same. So we have the covariance and actual error of the standard method. The red dot, this is on a 10 by 10 area. The estimations are sometimes outside of 10. This results snapshot after 1,000 steps. We have the red dot being the estimation location, the white dot being the real location, and the cloud being the error cloud. So here's the locale. We see locale is actually much more accurate. Not only that, we also see the variance actually mostly in cases of true error, or at least it's an indication of true error. But we really need a way to actually measure this, a way to actually quantify this. So using just the length of error actually doesn't capture the direction information. So instead, we actually use the area error. So this area error is actually calculated just basically drawing out all the errors, putting them on the same origin. And then once we do that, we just start drawing circles. Median circle encloses half the errors, then 75%, 25%, and so on.
Can you describe what was the step?
So every time step, you try to communicate. It may not always have a communication. The movement is actually random movement in the case I'm going to show you, but we also ran it on movement with ZebraNet movements. Random walk, right? So the percent error is actually this area circle divided by the field area. So here are the results, again, based on that. The case is 100 nodes over 100 kilometer by 100 kilometer area. That turned out with a combined movement model, we have an average of 0.24 neighbors per communication. So this is result of repeated 100 runs. So basically giving us 10,000 data points per time step. The results here are the vertical area show you the error, horizontal show you the time. The red show you the base case, the blue show you locale. So locale basically is actually a 21x improvement in median. And that brings us to less than 0.2% median error. What that means is that in this 10,000 square kilometer with only one beacon in the center, we're able to localize with an error about 2.5 kilometers. So decent given the random walk. So what happens when there's actually one node that, so what happens when not all nodes are well behaved? So this is probably the question you are wondering about. So this is the test of where one node have the absolutely worst error. And this worst error node have extreme certainty in its position. I think we can all relate to this, someone who's totally wrong, but so certain that he is correct. So the result is actually, we're actually able to correct the error much faster for this node because we actually spread out the error and all the nodes push this error into the GPS base. So errors are corrected much quicker. How did it do this? Well, because of movement model, because of movement, we actually spread out the GPS information. So errors sync to the location faster. This actually shows you the percent error and the distance away from the beacon. So we actually get 37x accuracy improvement at 10 kilometers, just based on the distance. And more than 10x even at the edges here. So it basically spreads beacon coverage. So what does that mean when you spread beacon coverage? It means you can actually reduce cost of infrastructure. Here is, again, beacon every 200 by 200 area, a beacon every 50-50, 30-30, 20-20, versus the blue, which is locale over 200 by 200 area, with one beacon over 200 by 200 area. So we see that locale is actually similar to a beacon every 30 by 30 area in the base case, which means we have a 40x reduction in infrastructure, roughly. So much reduced infrastructure. I'm sorry, I think I'm running a little late, but I'll just go to the conclusion here. So GPS-less localization in sparse network actually give us about 150 times lower power than continuous GPS and give us 21x reduction in median error compared to our base case. And infrastructure reduction, which means infrastructure reduction of 40x while maintaining similar accuracy. But more broadly, that collaboration in mobile sensor network, not just in localization, is a powerful technique for sharing information and to improve overall system capability. So what's next? I'm showing here the sensor design space, where vertical here you see the network dynamics, horizontal processor capability. I think applications are pushing more towards more network dynamics, and ZebraNet is one example. Moore's law is pushing us to more processor capability, and mobile phones are one example of that. And future mobile networks, I think, will have more network dynamics, like ad hoc communications, and more process power, basically due to Moore's law. That gives us a lot of opportunities. Why? Because we can have heterogeneous networks, both smart and dumb nodes. Smart nodes like your mobile phones, and dumb nodes like your RFIDs. I'm sorry if anyone doing research in RFIDs. But we're also not focusing on just delay-tolerant collaboration, but also delay-aware collaboration. Basically, because we have more processing power, we can actually learn the condition, learn the habits of users. We can actually maybe do some machine learning stuff on these limited devices. That'd be one interesting area. And because we also have newer actuator, newer batteries, sensor network doesn't actually have to just be passive observers, but they can actually start to do something. Maybe they can react to the environment, maybe self-deployed sensor networks, or maybe a relay station that have control movement. For example, cell phone coverage is low in this area, you pay someone to go there. So you can actually have control movement. Maybe you pay someone or a robot. So that'd be interesting. So my thesis contribution is actually moving towards this area with collaboration that does sparse and ad hoc, that improves sparse and ad hoc systems. So collaboration in localization, paper on that soon. Collaboration in automatic lifetime management, and also hardware-software sensor mobile delay-tolerant networks, basically ZebraNet. Got a couple of publications for that, and a couple of words. But the basic idea is that I'm taking this vertical approach to everything. For example, locale, the movement tracking, basically requires this middleware that does movement tracking and the hardware that actually have this directing system. So maybe too accurate. But basically, the global energy estimation, you also need energy tracking in the lower layers. And energy adaptation, you also need support of various layers. So basically, I think we really shouldn't be limited in a particular layer if we want to improve on something. So in summary, sparse mobile networks are here, important, and growing. Sensor networks are already here in wildlife tracking and various other tracking applications. Challenge networks such as rural and low infrastructure areas, and they're already here. And social applications like aging in place, some gaming applications, and future mobile phone applications. We're not quite there yet, but gosh darn it if I have anything to do with it. But the takeaway message, I guess, is that collaboration in these networks are not only possible, but they greatly improve overall system functionality. And with that, I can take any questions. Well, I should have slowed down.